Good morning. My name is Purit Kulworasreth, and today I will be presenting my research on the discovery of gallic acid as the first paracellular Claudin-2 channel inhibitor and its potential therapeutic for the treatment of colitis in mice. The epithelium and its cell junction, especially tight junction, play a critical role in forming a physical barrier that protects the internal body from external environment. Increased intestinal permeability contributes to inflammatory bowel disease or IBD pathogenesis, which can be mediated by tight junction dependent leak and pore pathway involving barrier-forming tight junction disruption and pore-forming tight junction overexpression, while tight junction independent apoptosis associated unrestricted pathway is seen in late-stage IBD. Tight junctions are not absolute barriers. Some tight junction proteins like Claudin-2 form paracellular sodium channels. And based on previous studies in intestinal specific Claudin-2 knockout mice, colitis did not develop in response to an inducer, suggesting that Claudin-2 serves as a drug target for IBD. Unfortunately, no Claudin-2 inhibitor is currently available in clinical practice. Recently, our group found that gallic acid can suppress leak pathway permeability via CAMKK, AMPK, SIRT1, and ERK-dependent mechanisms. However, its effects on Claudin-2-mediated pore pathway permeability and its potential application in the treatment of colitis has never been explored yet. Therefore, the main objective of this study is to investigate the effect of gallic acid on Claudin-2 channel activity, its underlying mechanism, and also provide the proof of concept that gallic acid is effective in the treatment of colitis. Currently, no cell line or cell-based assay is specifically designed to assess Claudin-2 activity. However, our lab has access to two intestinal cells, T84 and CACO2-BBE. The question is, how can we make it work? By identifying and leveraging distinct traits in these cells, we aim to develop a cell-based model to study Claudin-2 function. We observe transepithelium resistance, or TER, an indicator of tight junction integrity. High TER indicates compact tight junctions, while low TER indicates increased permeability via leak or pore pathways. T84 had higher basal TER than CACO2-BBE cells, correlating with the absence of Claudin-2 expression in T84 cells. The higher resistance may be due from the lack of Claudin-2 pores. However, we can't rule out other barrier-forming tight junctions yet. Thus, we did a permeability assay to confirm this. In this assay, we used two probes, fluorescein isothiocyanate of dextran in sizes 4 kilodalton and 70 kilodalton, 36 angstrom and 120 angstrom respectively. In healthy cells, with or without Claudin-2 expression, both sizes can pass through. If barrier-forming tight junction is destroyed, only 4 kilodalton can pass through. And with apoptosis, both sizes can pass through. After that, we will collect the sample from the basal side and measure fluorescence, which will give us the permeability rate. As a result, the permeability of 4 kilodalton dextran is the same for both cells, although TER is lower in CACO2-BBE. This means that barrier disruption didn't occur in CACO2-BBE cells, but might be due to Claudin-2 pores. Thus, CACO2-BBE might be a suitable intestinal cell to study Claudin-2 activity. In our molecular docking data, we found that gallic acid directly interacts with Claudin-2. Therefore, it might modulate pore function. If our prediction is right, if we treat gallic acid, the TER should be further increased in cells that express Claudin-2, which is what happened in CACO2-BBE cells. Furthermore, gallic acid suppresses Claudin-2 activity via AMPK, SIRT1, ERK-dependent mechanisms, the same pathways that gallic acid suppresses leak pathway permeability. To study its potential application in colitis, we used a DSS-induced colitis mouse model where we investigated the clinical outcome and molecular analysis of colonic tissue from DSS-induced mice. We found that gallic acid attenuated all clinical manifestations of colitis, including weight loss, disease activity index, shortening of the colon, and enhanced survival rate. Gallic acid also reduces immune infiltration and decreases goblet cell number, which are hallmarks of colitis. It also suppressed neutrophil activity, which we measured using myeloperoxidase activity assay, and suppressed interferon gamma and tumor necrosis factor expression. Interestingly, gallic acid significantly reduced Claudin-2 mRNA and protein expression in colitis mice, but had no effect on barrier-forming tight junction Claudin-1. In addition, gallic acid significantly increases AMPK and ERK phosphorylation, as well as enhances SIRT1 activity in colonic tissue, which is consistent with our previous finding that gallic acid also suppresses leak pathway permeability via the same mechanism. Our findings were also consistent with a previous study from another research group that ERK suppresses Claudin-2 expression in Madden Barbie canine kidney cells. So in conclusion, this study provides the first evidence that gallic acid acts as a Claudin-2 suppressor, which may be beneficial for treating various diseases such as colitis. However, translating to human clinical trial will require further investigation into its safety and efficacy. And lastly, I would like to give acknowledgement to Chulabhorn Royal Academy and National Research Council of Thailand for funding this research, as well as my advisor, Assistant Professor Pawin Pongkopsikun. Thank you.
Thank you very much for giving such a great presentation. Does any judges have any comments on your questions? Thank you very much. Please give our applause